Okay, so we are very happy today to have Yuma Mizuno from the University College Dublin. So he obtained his PhD from Tokyo Institute of Technology with research on cluster algebras. He is currently a postdoc at University College Dublin. He is also interested in lean theorem prover and is working on formalization of two-category theorem. Yuma, please.
Yeah, thank you for introduction. And first, I would like to thank organizers to give me a opportunity to give a talk in BIMSA-Tsinghua Quantum Symmetry Seminar. So, yeah, I will talk about the lean theorem prover and monoidal category theory. Okay. So, first, what is a lean theorem prover? So, lean is a theorem prover. So that means we can formalize mathematical definitions, theorems, and proofs in not natural language like English, but formal language, so lean language. And then lean can check the correctness of what we write. So this is a lean theorem prover. So there are many features on lean. So lean is based on dependent type theory with inductive types, not the set theory. And lean is a interactive code writing in VS Code text editor. So, and lean is a functional programming language, and it has powerful automation through called tool tactics. And there is a growing user-maintained mathematical library called Mathlib. And recently, so there are several research on integrating lean and AI. So, yeah, these are some features of lean. And in this talk, I will focus on some mathematical aspects of lean language. So I will give a brief review of what is theorem proving in lean. So what the theorem proving in lean means. So in lean, so mathematical concepts that we want to formalize are expressed as lean expressions called lean.express. And so lean's kernel does type checking on lean.express terms. And this type checking is used to formalize mathematical theorem and proofs. So that means if a lean express term H has a type P, and this P is also a lean express term, so such that P is a proposition. That means P has a type prop. So prop is a specific lean express term, one of the primitive term. And so in this setting, we can say that H is a proof of P. So the concept of what is proof is some expression is a proof of some proposition is a special case of type checking. So and Lean does that. And one point is that this Lean express term, at least its raw format, are almost not human readable or human writable. It is very computer language. And Lin's elaborator translates some human writable code into this Lin expert terms. So what the Lin user need to do is that, so they need to write human writable code, which is a certain form of like a programming code. Then Lin translate it into some more Mathline-like language, and Lin checks that. So this is correct or not. So yeah, this is an example, simple example. So defining some mathematical concepts, monoid. So this code define monoid in Lin. And I mean, this is a human readable code. So this is very readable. So I believe that you can understand what this means. So this obvious mean, so monoid is monoid structure of some type. Type means actually set in mathematics. So this means that monoid structure on the set M, it consists of the following 5 stuff. So the first is 1, which is a unit element, and the second is a mal. This is a binary operation. So you may be not familiar with this M2, M2M, but this is a way to express the binary operation in Lin. And the remaining 3 are axiom of monoid. And similarly, you can define what the monoid home is. So if M and N is a monoid, and F is a map from M to N, then monoid home, the definition of monoid home is that, so it maps 1 to 1 and multiplication to multiplication. Yes, this is very human readable code. And I would like to emphasize in this small example, the elaborator does non-trivial things. So for example, so look at this map mal condition. So this says that FA times B is equal to FA times FB. But so yeah, this what is this multiplication? So the first multiplication is a multiplication in M, but the second multiplication is a multiplication of N. So yeah, we can understand that, but we also understand this. So this is actual Lin code. So Lin can understand this, and that means so Lin can understand the first is a multiplication M and the second is a multiplication N, and this is one of the things the elaborator does. So this is an example. And these examples are definition of mathematical concepts. And this example is some proof. So yeah, this is some random equality in monoidal. Monoid. And we can prove this equality in this way. So this is a step-by-step proof. So just using monoid action in each step. Yeah, this is fine. But actually, in the paper proof, we usually do not want to write such a proof because we just want to say that this follows from the definition. So Lin also can. So how? So this is done by using a command called simp. So that means, so in in this equation, both sides are simplified to A times B times C times D times E, but the multiplication order is in this way. So this first attribute simple line tells Lin to what equation to apply the simplification. So that means, so this line says that, so using this simp tactic, then Lin uses these three actions to simplify the both sides of the equation and check that resulting simplified form is equal or not. And in this case, this solves the problem. So this is so simp. And then I would like to, yeah, I would like to give a comment of some info view. So this is one feature of in Lean. So we write Lean in the text editor. And many users use VS Code, which is one of the famous editor. And in VS Code, we can see the info view. So I usually put this tab on the right tab on VS Code. And so on the left tab, so I'm writing the Lean code. And this info view, so we can see the current status of the proof. So that means, so if we want to prove this theorem, then so the info view shows this information. So hypothesis and goals, which is very useful. And tactics. So a tactic is a command that manipulates the state displayed in the info view. So this is why Lean is called interactive theorem prover. So actually the info view so can be manipulated. And simple is one example of the tactic. This is a basic tactic in Lean which simplifies the current code. And there are many other tactics. Some basic ones, RW, which is rewrite tactic, or apply tactic, or intro tactic, and so on. And one important thing is that users can also define their own tactics. So this is an important point. So Lean is not only a theorem prover, but also a functional programming language. And tactics are written in Lean itself. So this is called metaprogramming. So meta means so, yeah. So writing some code that manipulate some Lean code itself. So these are tactics. And some remarks on tactics. So what you can expect from tactics? So they work as documented in most cases. So simplify the both sides, for example. And they don't claim to have proven something when they haven't actually proven it. So this is an important thing. So, and they pass some test cases. So on the other hand, what you shouldn't expect from tactics. So they're bug-free, or they always behave exactly as a programmer intended. Or they complete proofs within time limits, for example, in 10 seconds or 10 minutes or 10 hours. So yeah, tactics are actually not the mathematical proof. It's like a usual programming code. So this is one important feature of tactics. Okay. So this is a very brief review of Lean theorem prover. And from now on, I will focus on the formalization of monoidal category theory in Lean. So, okay. So formalization of monoidal category theory is developed in Mathlib. So user-maintained mathematical library written in Lean. And these are examples of concepts that have already been formalized. So definition of monoidal categories and lax monoidal functors and monoidal natural transformations, braided and symmetric monoidal categories, rigid monoidal categories, monoid object, comonoid object, bimonoid object, and hop object in monoidal categories, and Drinfeld center in braided monoidal categories. And yeah, there are some other concepts that have already been formalized. These are just examples, but yeah. And so for example, so this is a code using monoidal categories library in Mathlib. So the second line, so M type U and category M and monoidal category M. So this means that M is a monoidal category. And in this code, we set some parameters called universe. This is very useful to formalize some category theory stuff because yeah, some category, some category is not a small category, and some have in large universe. So and the link and some yeah, easily set some universe setting that can allow such a non-small category. And yeah, this is what parameter V and U mean. And so if we set this monoidal categories, M is a monoidal category, then we can use some notations. So like this tensor product notation. And so this is some random isomorphism in monoidal categories. Yeah, this is of course analog of the relation in the random relation in the monoid, but the equal is replaced by the isomorphism. So this A times B times 1 times C times D times E is isomorphic to this 1 times A times B times C times D times E. And yeah, this isomorphism is so composition of the isomorphism called associators and uniters. And this isomorphism defined in this way. So the sequence of isomorphism, and in each step is described by some associators or uniters. So this lambda means notations for left uniters in Lean. So this left uniters simplifies this 1 times C to the C. And these triangles is where indicates where to this left uniters apply. And similarly, this alpha means associators. So alpha ABC means this A times B times C, but first B times C is isomorphic to this A times B times C, but first A times B. And again, these triangles indicates where to apply this associator. So, and similarly. So this is an example of code. And okay. And in monoid case, one can use simp to obtain one-line proof. So what the monoidal case is, yeah, there is actually so one-line code that obtains a desired isomorphism. So this is obtained by this notation. So tensor one, this fancy notation is just some notation defined in Mathlib. So this represents the appropriate isomorphism. So the technical detail is that Lean synthesizes instances for the following type class. I will not explain what the type class or synthesizing or instance is, but yeah, just put some code. So so we define some notion called monoidal coherence between two objects. This is some chosen, that means some chosen isomorphism, and this notation means this chosen isomorphism. And what we actually do is so writing some special case to set desired isomorphism. And so after we writing this code, then Link tries to construct the isomorphism like this by using applying one of these constructions. Yeah, I will not explain in detail this, but yeah, this works anyway. But this is not the only point in monoidal category. So in monoid case, this is so in a sense, in monoid case, this is an equality. So obtaining equality is so final goal. But in monoidal category, this is not. That means there are many possible isomorphisms. So that means yeah. So for example, so this is one example, but we can have other isomorphism. So for example, in this case, so we first contract this one times C, but instead we can first applying associators to changing the position of the parentheses. So the isomorphism is not unique, but in the definition of the monoidal categories, we want to impose that eventually they are all equal. And actually, so there is a theorem called the coherence theorem. So that asserts that so these conditions, that means so these all isomorphisms are equal, follow from the specific two conditions called the pentagon and triangle identities. So these are pentagon and triangle identities. So what the meaning of this? So this is a pentagon identities. So that means if we start from A times B times C times D, but the tensor is in this order, and on the other, the final step is A times B times C times D, but the tensor is in this order, and we want to construct the isomorphism from this start object and this end object. And actually, so there are two ways to do that. So first applying associator and then applying associator, or first applying associator to this A, B, C part, and then applying associator, and finally applying associator to B, C, D part. So this length 2 step or this length 3 step. And the pentagon identities mean, so these tools are equal. And similarly, triangle identity is from A times 1 times B to the A times B. So first we applying right uniter to this A times 1 part, or first applying associator, and then applying left uniter to this 1 times B part. So triangle identity says that these are equal. And the coherence theorem asserts that in the monoidal definition of monoidal categories, so one only need to impose these two identities. Then other conditions follow from these identities. This is the coherence theorem. So yeah, so this is a coherence theorem. So in Lean, so what we need to do. So actually one can formalize coherence theorem. That means so one can define monoidal category expressions. So this is actually terms in free monoidal categories as a type in Lean, and formalize the coherence theorem as equalities in free monoidal categories. However, in practice, we need equality in arbitrary monoidal categories. And it is not obvious that one can translate the equality in free monoidal categories to the equality in arbitrary monoidal categories. This is, yeah, slightly annoying, but yeah, so this means that so we need to implement some tactic called coherence tactic that solves the coherence conditions automatically. So like tactic simp automatically solves the arbitrary equation in monoid. And there are two ways to implement the coherence tactic. So the first is so transporting equality from a formalized coherence theorem, which is so equalities in free monoidal categories. And the second way is so writing direct proof processing tactic. So actually, proof is some kind of Lean expression. Then we can write the code that manipulate so Lean expressions. So we can write some direct proof producing tactic. And actually, so we wrote both, and Mathlib's coherence tactic was based on the first method, but recently I rewrote it using the second one for some performance reason. And today, so I would like to explain so how this works. So in particular, I will explain so how to write direct proof producing tactic. So actually, the proof producing coherence tactic is based on the proof of the coherence theorem. In particular, given by so Bailey and Dividia. So Of course, the coherence theorem, you you may know coherence theorem is proved in the famous category theory textbook, category theory for working mathematician written by Mathlib. But the proof is actually much simpler. And so this is why I would like to implement their proof. The basic idea is to define normalization morphism by accumulator style recursion. So this accumulator style recursion is so their clever idea, which simplifies the proof a lot. So I will explain this. First, a normalized object is of the form of the following. So that means we first start from something and tensor to something from right, and this is the normalized object. And we want to define the normalization of object x, denoted by this bracket x. So for example, normalization of this a times b times 1 times c times d times e is equal to this form. So actually, the definition of the normalization, a normalized object, always start from 1 and tensor something to the right, and right, and right. So 1 times a times b times c times d times e. So this is the normalization. So yeah, actually, in paper proof, this is already a definition. But in Lean, definition is actually some more rigorous. But this example show what normalization means. And we also want to define the normalization isomorphism. That means isomorphism from the original one to the normalized one. So this is what we want. But in their accumulator style, we will not define this normalization directly. Instead, we define the normalization of n times x, where n is already normalized. So this is more generalized in the sense that if n is empty object, then this provides a normalization of x itself. But n can be an arbitrary normalized object. And we define the normalization of this pair of n and x. So this is accumulator style, and meaning so we think of n is already normalized part, and actually, so we define this by the structural recursion of x. So in the recursive step, x is simplified and simplified, and in a sense, the component of x is moved to the n, and finally, so n becomes the whole thing, and then we are done. So actually, definition is quite simple. The following is a definition of this accumulator style. normalization. So this is done by structural recursion on X. That means if X is a unit element, then normalization of n times X, n times 1 is n. And if X is actually tensor of X, tensor Y, then the normalization of this n times X times Y is defined as normalization of n times X. So normalization of n times X times Y. So this uses induction hypothesis twice. The first here and second here. And finally, for atomic X, that means it is not decomposed as a tensor. Then normalization of n times X is same as n times X. So this is the definition. Very simple. Then one can define the normalization isomorphism by structural recursion on X as well. So if X is 1, then n times 1, we want to construct isomorphism from n times 1 to its normalization. But by the definition, this n times normalization of n times 1 is n. So what we want to construct is isomorphism from n times 1 to n. This is, so we can say this is a right unit. And if X is actually tensor product X times Y, then this isomorphism is defined by the composition of this isomorphism. So first we apply the associator, then we apply the induction hypothesis to this n times X. Then, so we obtain a normalized form. So n times X. Then we are again using induction hypothesis to this normalized n times X and Y. Then we obtain the normalization. So bracket n times X times Y. And actually, by its definition of the normalization, this is a normalization of n times X times Y. Oh, the final one is actually equal, not just the isomorphism. But anyway, so we can use induction hypothesis twice to obtain this isomorphism. And finally, if X is atomic, then so n times X to the n times X, yeah, we can just put the identity. So in this way, we can define this isomorphism. So the definition is so very simple, and this is why accumulator style is useful. So because we can use induction hypothesis here and here, so which can, yeah, which can applicable because we have this n part. So actually, so we want to define this isomorphism in recursive way, but in that case, yeah, compared to the just define X to the normalization of X. So that means if we don't have n, then we have less induction hypothesis, so it means that it is more difficult to construct such isomorphism. But if we have n, we have more strong induction hypothesis and very easy to define such isomorphisms. This is one point. And so after defining normalization isomorphism, the coherence theorem actually follows from this single lemma. So suppose that we have isomorphism from x to y, made up only of associators and unitars, and actually or identities. So that means normalization of x and y is the same, and f is some associators like isomorphism. Then consider the following isomorphism. So first applying f to the from n times x, first applying f to this x part, then we get the n times x. And then we composing the normalization isomorphism to obtain the normalization of n times x. So we obtain the morphism from n times x to the normalization of n times y. The statement that this is equal to the normalization isomorphism to the n times y itself. So now, from the assumption, normalization of n times y is equal to normalization to the n times x. So the domain and the codomain is the same for these isomorphism. And this lemma states that actually these isomorphisms are equal. And then we now see that this key lemma actually implies a coherence theorem. So first assume that we have two isomorphisms from x to y, made up only of associators and unitars. And so we need to prove that f is actually equal to g. But the key lemma, both isomorphism from n times x to the n times y. But first isomorphism is defined by using f, and the second isomorphism is defined by using g. But the key lemma says that both are equal to the normalization of the n times x itself, which does not depend on f or g. So these are equal even times y to its normalization. Then we have f is equal to g. So this is a coherence theorem. So yeah, so this key lemma implies a coherence theorem. So how to prove this key lemma? This is structural induction on the morphism f. So that means, so f is associators or unitars or composition of these things. So with induction. So for example, if f is a single associator, then what we need to prove is that so composition of this isomorphism is equal to the composition of this isomorphism. So this is two isomorphism in the key lemmas. So we need to prove that these are equal. But so if you carefully write these isomorphism, then so you can see that this follows from pentagon identities. And several other action in monoidal category actually, but to prove this, yeah, we need to use pentagon entities anyway. So, and other cases are similar. So that means, yeah, so this is the in the example, so I saw a singular associator case, but there are other many cases. So for example, inverse of associator or left uniter, right uniter, or composition or tensor of these things. But one can actually prove that these two isomorphisms are equal. And one remark is that so composition or tensor cases, so use induction hypothesis. So this is actually induction proof. But proof is very explicit. So it tells that how to obtain the actual equality between two morphisms. So the main algorithm of the coherence tactics implemented in Lean is a recursive function that generates the equality of the key lemma. So this is the content of the coherence tactic. So in a sense, it extracts some algorithmic part of the proof of the coherence theorem. So this is coherence tactic. And that's all of the talk. So I would like to introduce practical use of coherence tactics in Mathlib. So there are several tactics relating the coherence theorem. The first one is a monoidal coherence tactic. So that solves any coherence condition. So this is a tactic that so I explained. And actually there is a more powerful tactic than that called a monoidal tactic. And in practice, one need to use a coherence monoidal tactic and always use this more powerful tactic. So which solves equalities between morphism in monoidal categories. So whenever they have the same string diagram. So string diagram is one way to express the morphism in monoidal category in diagrammatic way. But actually the expression corresponding to the same string diagram is not unique a priori, but the monoidal tactic proves that so different expressions are actually the equal. And there is a related tool called the string diagram widget that displays the string diagrams in the info view. So in practice, so one can use a string diagram widget to show a string diagram. And when proving the identity in the monoidal category, then if the string diagram of the left-hand side and right-hand side are same, then one can solve this by monoidal tactic. So this is one example in Mathlib proof. So this is a screenshot. So the resolution is slightly low. Sorry about that. But and this is some actually the complicated monoidal category stuff called the Joinfeld center in the braided monoidal category. Monoidal category. And I will not explain what that means, but if we use a string diagram widget, then it tells that this theorem is equality between something like this. So that means, yeah, in a sense, so this equality means that this f dot f morphism can pass through the this braiding morphism and obtain this right hand side. And actually, but yeah, so in paper proof, this is very obvious because I didn't explain what the center is, but one axiom of it contains f can pass through this. So this is almost obvious by the definition. But in Lean, this is not quite obvious, but because these diagrammatic expressions, we ignore something. So something means associators or uniters. So for example, so in this string diagram, so have three string, but this means actually so we have associators between so these places, but this ignores such things. So actual proving in Lean is more complicated, but monoidal tactics helps a lot. So we use monoidal tactics 3 times in the proof. So so what we need to do is that so we write expressions and see some to and see string diagram by using string diagram widget. And if the left hand side and right hand side is equal, then using monoidal tactic to solve that. So this automatically use coherence conditions. So which is not obvious to obtained by manually, but coherence tactic automatically can. So this is one example of the practical use of coherence tactic. Yeah, okay, that's it. This is end of my talk, and thank you for listening.
Thank you. That's a good question. Speak. Yeah.
Okay. Hi, Yuma. This is Harry from BIMSA. Nice talk, and I have a question about your recursive algorithm. One of the steps is to decide whether a object X is atomic. But how do you define the object in Lean? Like, what's its type? What's the type of an object, and how do you decide if it's atomic?
Oh, this is very interesting. Important question. Yeah, this is very actually the one. Yeah, one involves some technical details. In the coherence tactic, so yeah, for example, so in this case, obviously A, B, C, D, E, and atomic, but in a sense, this is not formally defined. That means so that means tactic is like a program. This is not the mathematical definition of proof. So the simple answer is that so determining given object is atomic or not is some heuristic one. And what actually the tactic does is that some pattern matching on the expression. So for example, so if this expression is given, and so in rolling expression term, so this is expressed as application of the tensor product to these two objects, so left one and right one. So internal in Lean, so this means that this Lean expression is tensor to the something to something. So tactics sees this expression and checks that this expression is some application of the tensor object to something to something.
Okay, I see.
So this is what actually does.
So the expression is seen by the tactic as a syntactic object instead of a semantic object. By syntactic, I mean, so A, B, C are like a black box. They don't care about what it really is. So it's just a and they're treated as atomic.
Yes.
I see. Thank you.
I have several questions.
Sure.
So can you explain what is the difference between Lean and, for example, another software like Coq? Well, what's the point of Lean in difference with Coq, for example?
So actually, so I explained some feature of Lean. Actually, Lean is so in a sense slightly similar to the Coq language, Coq theorem prover. So that means Coq is also based on dependent type theory with inductive types. But of course, there are many technical differences. But for me, so the main difference is some community around the theorem prover. That means so community means users. So in Lean, the community is more oriented to the pure mathematical. That means, for example, this Mathlib contains so much more pure math oriented math libraries than other theorem provers. So that means so Coq is more oriented, computer science oriented, and so at least for me. So and also Agda is more computer science or more homotopy type theory stuff. But Lean is more oriented to the traditional pure mathematical So, I'm a mathematician, so it's more easy to learn lean than other proof system, other theorem provers.
I see. Okay. So other question. So lean is called a theorem prover. So in what sense is proving theorem? Regarding your talk, you are implementing yourself the proof. The software is not proving itself the theorem. So why it's called theorem prover and not theorem proof checker or something like that?
Yeah, actually, yes. Theorem prover or proof system is the whole package of the actual large software. And actually, but it contains a kernel elaborator. Kernel checks the proof in a sense, but elaborator helps proving or assist in some way. And in a sense, tactics is also proving something or assist. For example, this simple proof is not applicable in paper or paper and pen proof, so we can't do simple in paper. So that means when using tactics, so sometimes we don't need to understand what actually going on. Just write tactic command, and if this succeed, then we can trust that. And actually, we can see what is going on by seeing actually rolling space-time, for example. But this is one feature of the theorem prover.
So it's like an assistant, as you said. It's an assistant.
Assistant.
So the other question is, what about using AI to transform a LaTeX proof into a lean proof? Or if you use, for example, I don't know, any AI, you ask him, take this LaTeX proof and make it
this is very
proof. What is this working or not? Or not yet?
Yeah, of course, interesting topic. And yes, and actually, I am not the expert on AI or machine learning, so I can't say some technical or precise statement. But just as a user, so yeah, it's great if this works, and there's several research about that. But for users, I haven't used the AI tools a lot. Oh, except for the GitHub Copilot, which is actually very useful to write lean code. But other than that, so I don't have much ideas what the current status is. So it can write complicated mathematical definition, or at this point, more elementary stuff like so Math Olympic, IMC problem, or so I'm sure, but this is obviously one of the hot topic recent in these days.
Fine. Last question is, so what is the goal
Lean, if the goal is to encode all the mathematics so all this library will be enriched by all the mathematics. So the goal is to cover all the mathematics and to check all the proof. What is the goal of the end?
Yeah. It's in a sense of course, there is no specific goal, like no goal of science or no goal of mathematics. But of course there can be some milestones like proving very important theorem in mathematics that have been not formalized in Lean or any theorem provers, and also formalizing mathematics that cannot be written or explicitly written in paper proof. For example, that is too long without the automation proof like SIMP, or some restrictions to the traditional style. So the goal may be, of course, have many directions.
What is your favorite goal for you personally in the future?
Yeah.
What do you want to go?
For me, so one of my interests is filling the gap in the paper proof and Lean proof. So, for example, in this monoidal category case, so in paper proof, so one usually ignores associators and uniters by coherence theorem, we can ignore that. But actually, in formalized theorem prover, this doesn't work. So, for example, one thing I'm familiar with about the monoidal category is Yang-Baxter equation, which says that some called operator R, which is isomorphism from V tensor V to the V tensor V, and Yang-Baxter equation is something like R times identity, a composition of R times identity and identity times R, and R times identity is equal to the similar morphism obtained by opposite tensor. But this actually contains the associator, so R times identity and identity times R cannot be composed in the formalized system. So, of course, we can write the explicit associators, but when we want to prove some theorems about the Yang-Baxter equation and the R matrix, then these associators always exist in the expression, and this is quite annoying in actual proving. So, so one of my motivation is that removing this annoying stuff automatically using tactic, which is obtained by one Lean's key feature functional programming language aspect. This is one of my motivation. Of course, this is not only one, but yeah.
Okay, thank you. Any other question? Online, no question. Okay, thank you again.